Hi everyone and welcome to tutorial 3. In this tutorial we're going to continue our discussion of multiple linear regression, including confounding and collinearity, but we'll also introduce effect modification or interaction, and we'll go over how to choose the best model and the steps for fitting a multiple linear regression model. This is just a quick reminder about the steps for hypothesis testing. So whenever you're asked to conduct a hypothesis test, for example, examine the differences between groups, you should make sure that you address all of these steps. So begin with an assumption and clearly state your hypotheses, make sure your assumptions for hypothesis testing are met, calculate a test statistic and confidence interval, calculate a p-value, and reject or fail to reject the null hypothesis. And you should also be clear about what led you to reject or fail to reject the null hypothesis. So was it the p-value or the confidence interval? So first let's start with a quick recap of confounding. Remember that in order for a variable to be considered a confounder, this should make sense both theoretically and statistically. So theoretically, does it make sense that the variable is associated with the primary x variable, a predictor of the outcome, and is not on the causal pathway? So as an example, let's revisit our discussion of the association between smoking and FEV from the last tutorial. So conceptually, do you think gender could be a confounder? Is it associated with the primary explanatory variable, smoking? It could be, so depending on your population, it could be that men are more likely to smoke than women or vice versa. And you could check this relationship numerically with bivariable analyses, so with something like a mosaic plot or a chi-squared test, or by estimating an odds ratio and associated confidence interval. And conceptually, do you think gender could be a predictor of the outcome, FEV? Most likely, it could be that women have lower FEV than men on average. Again, you could check this with bivariable plots or tests. And is gender on the causal pathway between smoke and FEV? Does smoking lead to gender, which then impacts FEV? No, this doesn't make sense. So conceptually, gender seems to meet our criteria as a confounder. The next thing to check is if gender confounds the XY relationship statistically in your dataset. So remember, the rule of thumb is that if there is greater than a 10% change in beta 1, so the slope for your primary x variable, when you add the potential confounder to your model, this suggests that the variable is a confounder. So we've said that theoretically it would make sense for gender to confound the association between smoking and FEV. So let's see what happens when we add gender to our model from the last tutorial that included age and smoke as predictors. So our new model output is shown on the top with gender added, and our previous model is shown on the bottom. Remember that because we're interested in the relationship between smoking and FEV, we look at how the beta for smoking changes with the addition of gender. So let's compare the change in beta 1. 0.21 minus 0.15 divided by 0.21 equals 0.29. So our estimate of beta 1 decreased by about 29%. So it looks like gender is a confounder, and this makes sense theoretically and statistically. So we would conclude that we should adjust for gender by keeping this in our regression model. So now we'll turn to effect modification or interaction. And these terms have slightly different meanings, but for the purpose of the course can be considered the same thing. So effect modification occurs when the relationship between an x variable and a y variable depends on the value of a third variable, which is known as an effect modifier. So for example, the effect of smoking on FEV depends on gender. This means that the slope of the regression line is different for men and women. So let's say we're interested in fitting a model with two explanatory variables, where one of these is categorical and the other is numeric. So for example, let's say we want to look at the effect of age on FEV for smokers and non-smokers. This is essentially like we are fitting two regression lines, one for smokers and one for non-smokers, but rather than fitting two separate equations, we fit one model, which gives us two separate regression lines. There are 4 things that can happen when we model this. So smokers are red and non-smokers are blue. On your top left is a model where smokers and non-smokers have the same intercept and same slope. This model is saying that smoking is not important. The lines are pretty much exactly the same. In other words, there is no difference between smokers and non-smokers adjusting for age. On your top right is a model where the two lines have the same slope but different intercepts. This model implies that non-smokers have a higher FEV than smokers adjusting for age. This assumes that the slope for the effect of age on FEV is the same for smokers and non-smokers, which is the same as assuming that the effect of smoking on FEV is the same across age groups. In this situation, the bias due to age confounding is removed. So we can answer the question, what is the effect of smoking adjusting for age? We can say that the effect of smoking is independent of age. The difference between smokers and non-smokers is the same at each age. The effect of smoking does not vary by age. The rate at which FEV increases with age is the same for smokers and non-smokers. So in other words, smoking and age both act independently on FEV. On the bottom left is a model where the two regression lines have the same intercept but different slopes. So in other words, non-smokers and smokers start the same, but age changes the relationship over time. This is a special case that doesn't happen often in reality, so we're not going to discuss this in the course. And on the bottom right is a model where the two lines have different slopes and different intercepts. This model implies that there is an effect modification, or that the variables age and smoking interact. The rate at which FEV increases with age is different for smokers and non-smokers. So the effect of age is modified by or depends on smoking. It can also be stated that the effect of smoking is modified by or depends on age. Both are correct. In statistical terms, we can say that the variables age and smoke interact with one another. So with confounding, the effect of x1 is stuck with x2, but with effect modification, the effect of x1 depends on x2. So what do you think? Is it reasonable to think that smoking could change the relationship or the slope of the line between age and FEV? You want to think this through both theoretically and statistically. So I think it's reasonable to think this. So for example, with children or teenagers, like those in the dataset, FEV likely increases with age, but the rate at which FEV increases with age, or the slope of age, could be lower for smokers than for non-smokers. So what about checking for effect modification statistically or numerically? Recall in SPPH 502, how did you determine whether or not effect modification was present? As a hint, think about 2x2 tables. Let's go over an example. This shows example data looking at the relationship between shift work and cancer. The CRUDE risk ratio for the association between the exposure and cancer is 4, but when stratified by regular or irregular shift work, the risk ratio is much higher for the irregular group compared to the regular group. So the irregular group has a risk ratio of 23.5, while the regular group has a risk ratio of 1. So this suggests effect modification. The effect of the exposure on cancer is modified by shift work. The effect of shift work on cancer depends on whether or not it is regular or irregular, with a strong association between shift work and cancer among those who work irregular shifts, and no association between shift work and cancer among those who work regular shifts. So how do we check for effect modification in a multiple linear regression model? There are two ways. The first is to fit a model for each level of the effect modifier. So for example, one for those who do regular shift work and one for those who do irregular shift work. This works well for categorical variables, but not so much for continuous variables, because you would need to fit a model for each level of the continuous variable. So if you're wondering if age was an effect modifier, and you had a sample whose age ranged from 1 to 60 years old, you'd have to fit 60 models. Or you could categorize your continuous variable in some way. The second option is to add an interaction term to your model. This means that in addition to having variable 1 and variable 2 in your model, you also include an interaction term, so variable 1 times variable 2. This works with either continuous or categorical variables, but interpretations are more difficult. So let's turn to an example. First, let's try fitting models stratified by gender. The top model is restricted to men, where gender equals 1, and the bottom model is restricted to women, gender equals 0. So how would we interpret the coefficients for smoking in these models? We would say that male smokers have an FEV that's an average of 0.17 liters lower than male non-smokers, adjusting for age. And we can also say that among males, smokers have an FEV that's an average of 0.17 liters lower than non-smokers, adjusting for age. For females, we would say that female smokers have an FEV that is an average of 0.06 liters lower than female non-smokers, adjusting for age. Or we can say that among females, smokers have an FEV that is an average of 0.06 liters lower than non-smokers, adjusting for age. Now let's try fitting a model with an interaction term. You can see that whenever we add an interaction term to our model, we keep the original variables in as well. For example, here we keep smoke and gender in the model in addition to an interaction term of smoke times gender. So how do we interpret these coefficients? This is a little bit trickier, and this will become easier to do the more you practice it, but when learning, the best thing to do is to write out the full regression equation. So one equation for each level of the potential effect modifier, one for women, gender equals 0, and one for men, gender equals 1. So let's start with the top equation for women. In the equation, our gender equals 0. So we insert 0 into the equation in place of the two values for the gender variables, for both of the coefficients for gender and the coefficient for the interaction term that includes gender. We can then scratch off or delete anything that includes gender from the regression equation because these will equal 0. So let's turn to the bottom equation for men, when gender equals 1. So we insert 1 into the values for both coefficients in the equation that include gender, so both the gender coefficient and the interaction term between smoke and gender. We can then add our intercept of 0.26 plus 0.28 to get an intercept of 0.54, and then add the negative 0.10 smoke to negative 0.07 smoke to get a coefficient of negative 0.17 smoke. So for men, smoking is associated with an average of 0.17 liter decrease in FEV, adjusting for age. And for women, smoking is associated with an average of a 0.07 liter decrease in FEV, adjusting for age. This is a simplified visual example of what we just calculated. So the regression line for men is blue and red for women. And this shows the reduction of FEV for smokers compared to non-smokers. We can see that smoking is associated with a reduction in FEV for both women and men. But the reduction in FEV appears to be more pronounced among men compared to women. The slope is steeper for men than women. In other words, the effect of smoking on FEV seems to depend on gender. Gender appears to act as an effect modifier of the association between smoking and FEV. But how do we check if our interaction term is significant? How do we know that this difference in the effect of smoking between men and women is different enough that we can claim that the effect of smoking varies by gender? We could look at the p-value of the interaction term in the model summary output, but it may not be significant even if the interaction term is. So it's better to use the partial f-test. Remember what we said in the last tutorial, that the partial f-test can be used to compare nested models only. In this case, we are comparing the full model with the interaction term to the reduced model without the interaction term. Our null hypothesis is that the sum of squared error of the full model with the interaction term equals the sum of squared error of the reduced model. Our alternative hypothesis is that the sum of squared error of the full model is less than the sum of squared error of the reduced model. The full model is better. Here's our output from the partial f-test. Since the p-value associated with the f-statistic is less than 0.05, we can reject the null hypothesis that there's no difference between the models and conclude that we have evidence to suggest that the full model is better. The full model explains significantly more variation than the reduced model. So we should keep the interaction term in our model because this suggests that the effect of smoking on FEV is modified by gender. Remember that effect modification is a source of bias. If we didn't detect the interaction that we just did, this would bias our results. Because if we just adjusted for gender and didn't detect the interaction, we would wrongfully infer that the effect of smoking was the same for men and women, when this isn't the case. Of course, it's difficult to theorize and examine any and all potential interactions, but we want to do what we can to try to detect those that we think might be theoretically plausible. So this is just a summary of how we fit a linear regression model. Remember that this is a process involving moving back and forth, testing different models, assumptions, adding, dropping variables, testing model fit, and so on. As Mike says, model building is half science, half art. There isn't one right way to fit a model, but there are different approaches that we will discuss. And in the next tutorial, we'll walk through this process to answer a question using the HERS dataset. The first step in fitting a model is to identify the goal of your model. Is it predictive or is it a comparative model? Predictive models seek to understand which x's give the best estimate of y. Comparative or effect size models answer the question which x's are needed to give the least biased estimate of beta 1. For example, what's the effect of smoking on FEV? And we add confounders if we think it will remove bias from this estimate. You then want to identify your primary, explanatory, and outcome variable and review the other variables that you have in your dataset, including how these are coded. Could these confound your association of interest or modify the effect? Do we have all the variables in our dataset that could potentially confound or modify the association of interest? For example, we don't have a measure of fitness in the smoking and FEV dataset. This could be an important confounder or effect modifier. The next step is to look at the univariate distribution of all of your variables. So this will allow you to learn more about distributions and identify missing data or potential errors in your data. Next, take a look at the bivariate associations between your explanatory variables and outcome, and the bivariate associations between your primary explanatory variable and other explanatory variables. You want to check any hypotheses that you may already have about the relationships between variables. The next step is to fit your initial model. You can either start with all your variables that you think are important and try removing these, or you can start with a simple linear model and build up. So as you follow this process with each variable, you're trying to determine if you should keep that variable in your model. So you're looking to see if there's a change in your primary x variable slope and its standard error to determine if it's a confounder, predictor, collinear, or none of these. As you try adding or dropping variables, you should also compare models with the partial f-test or AIC-BIC to see if there's an increase in the variation explained by your model when you do so. If you find collinearity, you must decide which of the two variables to keep. And as discussed in the last tutorial, you may want to go with a variable that is a better known measure or is measured better, or you could use the AIC or BIC to compare models and use the model that has the lower AIC or BIC. And lastly, you'll want to check for effect modification, either with stratified models or by fitting a model with an interaction term and comparing it to a reduced model with the partial f-test or AIC-BIC. Remember that you should always have some conceptual or theoretical reason for including a variable in your model as a confounder or effect modifier. Once you've decided on a final model after following the steps that we've just discussed, you should then check your model assumptions. We went over how to check these with residuals and QQ plots in the first tutorial that focused on simple linear regression, but the same process is used for multiple linear regression. So you can check that video out for more information about how to check these assumptions. And as a side note, normality is the least concerning assumption to violate, especially if you have a large sample size. So what if you discover that your assumptions are violated? So first of all, what if the relationship between x and y is not linear? In this situation, you would usually transform x and or y to make the relationship linear. So usually you would log x or take the square root of x and then work with a transformed x variable. But the problem is that this makes interpretations complicated. For example, a slope would be interpreted as each 1 unit change in log of x is associated with an average increase of blank in y. So this isn't really all that intuitive for a reader to interpret. After you make any transformations, you'll then want to check your diagnostic plots to see if the issue is addressed and your previously violated assumption is now met. And you can also look at the AIC value to compare models with either the transformed or original variable. And the model with the smallest AIC is a better model. Another way to address nonlinearity is to use polynomial regression. Polynomial regression will allow you to fit a quadratic or parabolic shape. With polynomial regression, both x and x squared are included in your model. This is in contrast to a situation when we transform x, where only the transformed x variable is included in your model. So once you fit your polynomial regression model, you could then compare the AIC or use the partial f-test to see if this reduces the sum of squared error when compared to a model that only included x. Or you can rerun and check your diagnostic plots to see if the model with x squared fits better than the model without it. As a side note, we will usually center our x variable for the quadratic term in order to reduce collinearity between x and x squared. So if our x variable was height, this would mean that we would keep our original height variable in our model plus a quadratic term for centered height, so centered height squared. Another way to address nonlinearity is to create categories for a continuous variable. So you can review Mike's YouTube video on dummy or indicator variables for more information on this. And a final option for addressing nonlinearity is to fit a nonlinear regression model, but we won't talk about this here. If you examine your residuals plot and discover that the variance is not constant, you can use variance stabilizing transformations. Usually you'll want to log y or take the square root of y to stabilize the variance. This does complicate interpretations though. So for example, slopes would be interpreted as the average change in logged y with each 1 unit increase in x. As a side note, if the constant variance assumption is violated, our confidence intervals will be affected, but our slope will not be biased. So if we just want to interpret the slope of the line, we're okay. Our line represents the relationship of x with y, or how changes in x affect y. But if we want to try to make predictions, assuming constant variance in our model is going to be an over or underestimate of our variability. This is where the non-constant variance assumption being violated is more of an issue. But if we just want to interpret the slope, it's okay because this won't be biased by non-constant variance. So once you've done your transformations, you'll want to check that the problem has been addressed and see if you need to make any further adjustments. Fitting models is a back and forth process, not a simple checklist. We want to produce a model that fits best, but we need to understand that there's always potential for bias in our model. In the next tutorial, we're going to recap and expand on multiple linear regression and conduct a practice multiple linear regression analysis with the HERS dataset.